Let's look at a hypothesis test for a mean. We've been told that the mean body temperature for healthy adults is 98.6 degrees Fahrenheit. But is that true? Well, let's find null and alternative hypotheses. Note that this is a hypothesis test for a mean, not for a proportion, which we saw in the previous chapter. A hypothesis test for proportion looks like this. We want to test the hypothesis that the proportion of successes is such and such. In other words, the proportion of college students who are female is 57%, or the probability that a coin lands heads is a half. That's like the proportion of heads is a half. Or more than 1/2 of full-time college students are commuters, or a die is fair. In other words, the probability of each side coming up is equal. The null hypothesis, as always, means no change, no difference. It has an equal sign. So it's going to be of the form mu equals mu0, like mu equals 12, something like that. Again, it's going to be mu equals and not p equals because we're dealing with means and not proportions. The alternative hypothesis means there is a change, there is a difference. So the alternative hypothesis will be of the form mu does not equal something, or mu is greater than something, or mu is less than something. Okay, so here our null hypothesis is that mean body temperature for healthy adults is 98.6 degrees Fahrenheit. So here's the way we represent that symbolically. Let y equal the body temperature for healthy adults in degrees Fahrenheit. The null hypothesis is that mu equals 98.6. As for the alternative hypothesis, well, mu is less than 98.6. We would choose this as the alternative hypothesis if we wanted to test the hypothesis that the mean body temperature for healthy adults is less than 98.6, not what we want. Mu is greater than 98.6, we would choose this as the alternative hypothesis if we wanted to test the hypothesis that the mean body temperature for healthy adults is greater than 98.6, not what we want either. Mu does not equal 98.6. We would choose this as the alternative hypothesis if we wanted to test the hypothesis that the mean body temperature for healthy adults is different from 98.6, or if we wanted to test the hypothesis that the mean body temperature for healthy adults is is 98.6. And that's what we want in this case. Mu does not equal 98.6. We choose this as the alternative hypothesis because we want to test the hypothesis that the mean body temperature for healthy adults is 98.6. So here's the way we'll represent it. Y is the body temperature for healthy adults. The null and alternative hypotheses are here. Okay, we want to do a hypothesis test for a mean. Do the data satisfy the required conditions? Here are the conditions for using the hypothesis test for a mean. First, the data have to come from a random sample. The sample has to be less than or equal to 10% of the population. If you have a sample that's bigger than that, you can still do a hypothesis test, but you need to make some adjustments, and that's beyond the scope of this course. The distribution of the data is nearly normal. So when n is less than or equal to 15, it's unimodal and symmetric. There are no outliers and it's not skewed, so maybe again something like this. When n is between 15 and 40, it's unimodal and more or less symmetric. And when n is greater than or equal to 40, it just has to be not extremely skewed. So notice we get less and less picky as n grows larger. And if there are outliers, try eliminating them. If you eliminate them and it improves the model, well, then go ahead and leave those out. Okay, so here are our null and alternative hypotheses. A sample of 106 body temperatures of healthy adults yielded a sample mean of y bar equals 98.2 degrees with a sample standard deviation of s equals 0.62 degrees. Calculate the test statistic, t. Okay, so t is y bar minus mu0 over s over square root n. Recall that mu0 is the conjectured value of mu in the null hypothesis. So in this case, that's our mu0, and that's what we plug in here for mu0. Okay, so t equals y bar, which we were told is 98.2 degrees, so plug that in here, minus mu sub 0, we were told that's 98.6, and that comes from here, over s, that's the sample standard deviation, over square root n. Well, n in this case is 106, so that would be over square root 106. And that equals 6.64. Well, what does that mean? This is what a normal distribution looks like. We've seen this before. This is what the distribution of our test statistic t equals y bar minus mu sub 0 over s over square root n looks like. It's also called student's t. The man who developed it was named Student. Actually, that was just his pseudonym. In this case, notice that t t takes on, there's not just one t distribution, there are lots of t distributions, and they all depend on the degrees of freedom, which is simply n minus 1. Now, in our particular case, n is 106, so n minus 1 is 105. So the degrees of freedom in our case is n equals 105. Okay, so here, for example, I don't have n equals 105. I don't have df equals 105, but here's what the distribution would look like if t, the t distribution, if we have 1 degree of freedom, the red one is 5 degrees of freedom, etc. So there are different t distributions. Okay, here's what I'd like you to notice. We'll compare the t and the normal. Compared to the normal distribution, the t distribution is a little fatter in the tails. Look especially at 1 degree of freedom. Okay, this blue one, see? That's a little fatter in the tail than the normal distribution. The normal distribution is this one that's on top. So that's the blue one. Whereas this other one, that's the one that's on. This other one, a little fatter in the tails here. And also, as n approaches infinity, the t distribution approaches the normal distribution. You can even see that here, because notice, as n gets larger, in other words, as the degrees of freedom get larger, these get closer and closer to that top curve, which is the normal distribution. With a hypothesis test for proportion, which we saw in the last chapter, when the alternative hypothesis was two-sided, we rejected the null hypothesis when the z-score was too far to the left. Z was less than negative 1 points, I'm sorry, this should be over here. Z is less than negative 1.96, or when the z-score was too far to the right. Z is greater than 1.96. With a hypothesis test for a mean, when the alternative hypothesis is two-sided, we reject the null hypothesis when t is too far to the left or too far to the right. But we don't use not 1.96. That's just for the normal distribution. Instead, our number depends on the degrees of freedom, which is n minus 1. Okay, let's look at the t distribution table. It's the fourth table in Appendix D of our textbook. Here's how you can access it. You can go to Course Tools. So again, go to Course Tools and choose HTML ebook. Okay, then open the alternate version of your ebook. Click on that. And then open an HTML version of your textbook, and then Appendix D, Tables and Selected Formulas. And then use the right arrow to advance to the fourth table. So in other words, once you've opened the ebook, you choose this, Appendix D, and then you click on this arrow, until you get to the fourth table. And your fourth table should look something like this. Okay, let's blow this up. Wow, this is a scary table, but you can do it. We can do it together. Okay, this is a two-tail test, and the two-tail probability is 0.05 because we want 95% confidence, and so that means the stuff that's left over in the tails is 5%. So two-tail probability, 5%, that means we're working with this column here. Okay, just look at this column. As for the row, that degrees of freedom is n minus 1, which is 105, so we want 105. So we go down, we need to keep going. Let's look at the rest of the table. Okay, here's the rest of the table. Now notice there is no 105 over here, but we always play it safe. We round it down. So in this case, we would go with 100. So we want the 100 row. So again, we want this column, two-tail probability 0.05, and we want this row, which means our value is 1.984. So the rule of 1.96 will be played by 1.984. In other words, T star equals 1.984. That's the equivalent of 1.96 when we're using a t distribution. But again, we're using that just because our degrees of freedom is 105. It's not always 1.984. It depends on n, the sample size. Okay, so another way you could do this is simply to enter t distribution table into a search engine like Google. That's another way you could find this table. Okay, so if the alternative hypothesis is mu does not equal mu 0, that's what we have, then the rejection region is going to be t is less than negative t star, or t is greater than t star. If the alternative hypothesis where mu is less than mu 0, the rejection region would be t is less than negative t star. And if the null hypothesis, or if the alternative hypothesis were mu is greater than mu sub 0, then the rejection region would be t is greater than t star. In other words, you'd reject if t is too big. Okay, since our alternative hypothesis is two-sided and of that form, mu does not equal mu 0, We reject the null hypothesis if t is less than negative t star or t is greater than t star. Again, t star is 1.984, so we reject the null hypothesis if t is less than negative 1.984 or t is greater than 1.984. And this is actually what the t distribution will look like when you have 105 degrees of freedom. So we'll reject it for t is less than negative 1.984 or t is greater than 1.984. Okay, here t equals negative 6.64, which is a lot less than negative 1.984. So we conclude that the null hypothesis is false. We reject the null hypothesis. There is sufficient evidence to conclude that the mean body temperature for healthy adults is not 98.6 degrees. Okay, let's find the p-value. What's the p-value? This is short for the probability value. It's the probability that we would get a result this extreme or even more extreme if the null hypothesis were true. So if the alternative hypothesis is mu does not equal mu sub 0, like what we have, we want twice the area to the right of absolute value of t. The alternative hypothesis is mu does not equal, mu is less than mu sub 0. We want the area to the left of t because this is what our distribution is going to look like. We want to reject only if t is too small. And if mu is greater than mu sub 0, we want the area to the right of t because we want to reject big values of t. Okay, but again, we have this first situation here. Mu does not equal mu sub 0. Okay, if the null hypothesis were true, the probability that t would be negative 6.64 or even more extreme. Okay, well, gee, what we need to do is find the area to the right of 6.64, and that's way out here. Oh my goodness, 6.64 is like over here. So how are you going to find that area? On the TI. So on the TI, go to Dister and choose TCDF. And you would enter TCDF A, B, DF. This is the left endpoint. This is the right endpoint. This is the degrees of freedom. So in other words, we would enter TCDF 6.64, 10. That 10 is the equivalent of infinity. I mean, 10 is close enough to infinity, right? And DF is degrees of freedom. That's 105. Okay, we get 7.0974 times 10 to the negative 10th. And again, for this hypothesis test, because it's two-sided, the p-value is going to be twice that, which is 1.419. Again, it's going to be twice that because we want twice the area to the right of absolute value of t. Okay, so the p-value is twice that, 1.419 times 10 to the negative 9th. Oh my goodness, that's small. So our p-value is 0.0000000001419. If the p-value is less than 0.05, we reject the null hypothesis. Because there's less than a 5% chance we would obtain a result that extreme or even more extreme if the null hypothesis were true. So again, if the p-value is less than 0.05, you reject. If p is low, the null must go. Oh my goodness, our p-value is so much smaller, so we definitely reject it. So this is what y represents. There are null and alternative hypotheses. We reject the null hypothesis. Because the p-value is so small, there is strong evidence that the mean body temperature for healthy adults is not 98.6 degrees. Now, if the p-value were close to 0.05, like 0.04, 0.06, then we'd say there's some evidence. If the p-value were big, like 0.25, then we'd say there is insufficient evidence. But here we can say there is strong evidence. Find a 95% confidence interval for the mean body temperature for healthy adults. Okay, for a hypothesis test from mean, the endpoints of the confidence interval are y bar plus or minus t star s over square root n. S over square root n, this is what we call the standard error of y bar. We represent it that way sometimes, and that's our estimate of the standard deviation of y bar. Okay, so plug in the numbers. Y bar is 98.2. T star we've seen earlier is 1.984. There's s over square root n, 0.62 over square root 106. And when you do the math, that ends up being 0.1. All this stuff ends up being 0.12. That's what we call our margin of error, because it's basically 0.12 on one side of 98.2 and 0.12 on the other side of 98.2. In general, for a hypothesis test for mean, margin of error is going to be this creature over here. Okay, so again, 98.2 plus or minus 0.12, that yields 98.08 and 98.32. Recall that earlier we rejected the hypothesis that the population mean is 98.6. This confidence interval result is in agreement with our hypothesis test because 98.6 is not in the interval. Again, we have a 95% confidence interval for the mean body temperature. 98.6 isn't in there, so we don't think 98.6 is the mean body temperature. Give a proper interpretation of the 95% confidence interval. There is a 95% chance that the population mean mu is in the interval.